Picture this, right? You are sitting in a really high-pressure AI and machine learning engineering interview.
Oh, the worst feeling.
Right. Your palms are, a little sweaty, the whiteboard marker's in your hand, or maybe your fingers are just sort of hovering over a shared coding environment. And the interviewer looks at you and asks the classic anchor problem.
Yep, the one we all know.
Exactly. Find two numbers in an array that sum to a specific target. So let's say your array is 2, 7, 11, and 15, and your target is 9.
Okay, I want you to stop right there. I want you to pause and think about how you will solve this interview coding question. Really think about it.
Yeah.
Can you just check every possible pair? What is the time complexity of that approach? Can you do better? Taking a moment to think before writing a single line of code, well, that habit of pausing is the habit of senior engineers.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
So glad to be here.
Yeah, so we are taking a deep dive today into the gap between two very different answers to that exact problem. Because the distance between a brute force O of n squared approach and an optimized O of n approach is quite literally the gap between a rejection email and a job offer.
It really is. And our mission today is to completely tear down that brute force method and replace it with O of n hashing.
Right.
We are going to build a rock-solid, highly intuitive mental model for solving frequency-based coding problems when you have a clock ticking down and an interviewer is analyzing your every architectural decision.
Okay, let's unpack this.
Yeah.
Because the intuitive place for our brains to go when faced with an array is, well, a nested loop.
Oh, absolutely. It's the human instinct.
Right. You take the first number and you iterate through the rest of the array to find a match. Then you step to the second number and, iterate through the rest of the array again.
But it is entirely flawed for real-world applications because of the O of n squared time complexity trap.
A trap.
Yeah, because when you are dealing with a tiny array of 4 numbers, checking every pair is trivial. It takes no time. But as an AI engineer, you are dealing with scale.
Massive scale.
Right. If you have an array of just 10,000 numbers, which, by the way, is a microscopic data set in machine learning.
Microscopic, yeah.
Checking every single pair means you are executing up to 100 million operations. Your CPU is just scanning and rescanning the exact same memory blocks over and over again.
It's awful. The classic analogy I like to use is sorting laundry.
Oh, I love this one.
Yeah, brute force is like picking up one single sock, holding it in your hand, and then checking it against every single other sock in a massive pile on the floor.
Sounds exhausting.
It is. And if it doesn't match, you put it down, pick up the second sock, and check it against the whole pile all over again.
Right. And the breakthrough here requires a total shift in how you process the data stream.
Okay, how so?
Well, instead of constantly searching forward through the array for a match, you have to store state. You maintain a record of what you have already processed. Ah, I see.
So your internal logic shifts from where is the match in the remaining data to have I seen the required complement in my historical data?
Right, the complement being the target minus the current number. So if the target is 9 and the current element is 2, you just need to know if you've seen a 7.
Exactly.
So in our anchor problem, the trace is incredibly fast. You evaluate the 2, realize you need a 7, and you check your hash map.
It's empty at first.
Right, it's empty, so you store the 2 and its index. Then when you move to the very next element, the 7, you calculate that you need a 2.
Yep.
You check your map, see the 2 sitting right there, and you immediately return the indices. You found the pair without ever scanning the rest of the array.
It's beautiful. That execution is clean, but there is a specific implementation bug that candidates write into this solution almost constantly.
Oh, what is it?
It comes down to the order of operations in the loop. You have to check the hash map for the complement before you add the current number to the hash map. Oh, because if you store the number first, you run the risk of matching the element with itself, right?
Precisely. If the target is 6 and you are evaluating a 3, adding the 3 to the map first means your complement check for a 3 will return true.
Wow, yeah. You end up returning the exact same index twice.
Which instantly fails the test case. You always check historical state first, then update the state.
That is a crucial tip.
But let's look at the underlying mechanics, because an interviewer isn't just going to accept that you used a dictionary and call it a day. They want to know why.
Actually, wait, I want to push back on the premise here.
Okay, go for it.
In Python, dictionaries carry massive memory overhead compared to a simple list. Under the hood, they allocate sparse arrays to maintain fast lookups. Okay.
Yeah.
So in a resource-constrained machine learning environment where we might be pushing, I don't know, GPU VRAM to the absolute limit with large tensors, isn't defaulting to an O-of-N-based complexity solution a dangerous habit? Why are we so eager to trade memory for speed?
That is a highly senior level concern, and honestly, it's exactly the kind of nuance an interviewer wants you to bring up.
Okay.
You are right that Python dictionaries allocate extra memory to maintain a load factor, usually keeping the underlying array only 2/3 full to avoid collisions.
Right, to keep it fast.
Exactly. However, the reason we make this trade-off is because of how compute-bound modern applications are. Memory is relatively cheap and scalable, but CPU cycles, those are your bottlenecks.
That makes sense.
But to justify that trade-off, you have to explain the mechanism of O of one lookup. How does a hash map actually achieve instant retrieval without scanning?
Right. It's not magic. It's just a mathematical calculation.
Totally.
It's less like searching through a library and more like having a magic ticket where the title of the book mathematically calculates exactly which floor, aisle, and shelf it sits on.
That's a great way to picture it.
You don't walk down the aisles looking at spines. You just walk directly to the physical coordinates.
That is the exact mechanism. When you pass a key into a hash function, let's say the number 7, the function applies a mathematical operation.
Like modular arithmetic.
Yes, often involving modular arithmetic against the size of the underlying memory array. That math spits out a specific integer which acts as the direct index in memory.
Wow.
The machine just jumps to that memory address. No iteration, no comparison loops, just raw, direct memory access.
But wait, what happens when two different keys run through that math and spit out the exact same index?
That is a hash collision. Python handles this using a technique called open addressing with probing.
Open addressing, okay.
Yeah, so if it jumps to that memory address and sees a different key already sitting there, it uses another mathematical sequence to jump to the next available slot.
Oh, I see.
This is why hashmap lookups are technically amortized O of one time. Occasionally, the system has to resize the underlying array or resolve a collision, which takes a few extra CPU cycles.
Right.
But on average, the lookup time remains constant regardless of whether you have 100 items or a billion items.
That is incredible.
Yeah.
And understanding that mechanism, modular arithmetic translating keys directly to memory addresses, that is what separates a coder who just memorized a syntax trick from an engineer who actually understands system architecture.
Exactly. And once you understand that mechanism, you can recognize when to deploy it. In an interview prompt, certain trigger words are massive, flashing indicators that you need this direct access memory model.
Trigger words like what?
Listen for phrases like pair sum, frequency, duplicate, exists, or any question asking how many times an element appears.
Here's where it gets really interesting. When you hit a frequency problem, there is a very specific implementation pattern you should use in Python.
Oh, golden template.
Yes, utilizing the .get method. If your dictionary is called freak, you update it by writing freak bracket x equals freak.get x comma 0 plus 1.
Such a powerful line of code.
It really is.
The .get method attempts to retrieve the current count for the key x. If x has never been processed before, it prevents a key error by returning the default value you provided, which is 0.
Nice.
Then it just adds 1. It handles initialization and incrementing in a single, safe operation.
Which totally avoids the trap of writing freak bracket x equals 1.
Oh, yeah, the fatal flaw.
Right, because if you hard code the assignment to 1, you aren't tracking frequency at all. You are just resetting the data to 1 every single time you encounter the element.
You destroy your own state with every iteration. It's a disaster.
Yeah.
But we also need to discuss precision. We keep referencing dictionaries and maps, which store a key value pair, but we also have sets, which utilize the exact same hashing mechanism under the hood, but only store keys.
Right, which brings up a good question. If they both provide that amortized O of one lookup, wouldn't it be safer to just use a map for everything? Like, why introduce a second data structure into your mental model?
That's a trap, too. Using a map when a set is structurally sufficient signals a lack of precision to an interviewer.
Oh, it does.
Yeah, it shows you don't fully understand your tools. A set just tracks existence. It asks, have I seen this before? A map tracks metadata. It asks, how many times have I seen this? Or where did I see it?
Okay, so if we are just checking existence, we can apply this logic beyond integer arrays.
Absolutely.
We can apply it to string manipulation. If an interviewer asks you to write an anagram check, determining if two strings contain the exact same characters, Well, that is fundamentally just a frequency problem.
An anagram is just a character frequency match, and you don't even need to write the .get loop manually for that in Python.
Wait, really?
Nope. You can just import counter from the collections module, which is a specialized dictionary designed specifically for tallying elements.
Oh, that's clean.
Yeah, you just write return counter string 1 equals counter string 2. It builds both hash maps and compares their structures under the hood.
Okay, but let's talk about the silent killers in these interviews.
Mm-hmm.
Because you can nail the core logic, build the perfect hash map, and still fail the technical screen because of edge cases and missing returns.
Oh, missing returns will get you every time. Let's use the duplicate check scenario as an example.
Okay.
You write a loop utilizing a set. As you iterate, you check if the current number is in the set. If it is, you return true. But what happens if the loop finishes entirely and you never encountered a duplicate?
Well, the function just ends. And in Python, it implicitly returns none, which is obviously not a Boolean.
Exactly.
You have to explicitly drop or return false outside the loop at the very end of the function.
The same applies to our anchor problem. If no valid two-sum pair exists in the array, you must return an empty array or whatever default they specified.
Because interviewers will aggressively test these boundaries.
Oh, they love to. They will pass in empty arrays. They will pass in arrays with a single element.
Yep.
You have to trace your logic through those boundary conditions to ensure your code doesn't throw an out-of-bounds exception or return invalid data.
And, writing the code is really only half the evaluation.
It really is.
The interviewer is grading your communication skills just as heavily as your syntax. You need a think-aloud script. You cannot write code in silence and just wait for them to guess your architecture.
Definitely not. You have to dictate the technical flow. Start by explicitly stating the baseline.
Right.
So you say, the brute force approach requires O of n squared time complexity due to nested iterations. Then you present the optimization. To optimize this, I will sacrifice O of n memory space to build a hash map, which allows us to store the state of previously seen elements.
I love that. You explicitly name the trade-off.
Yes, and then you explain the mechanism. Because hashmap lookups operate in O of 1 time via direct memory indexing, we reduce our overall time complexity to O of n, processing the array in a single pass.
That's perfect.
This script proves you understand the macro architecture of your solution, not just the micro syntax.
So let's scale this up a bit. We have focused intensely on arrays and single variables, but this O of 1 memory model is a foundational component of much larger algorithmic architectures.
It really is the bedrock.
Take the sliding window technique, for instance.
Oh, great example. A sliding window is used for processing contiguous subsegments of data. Imagine an interviewer asks you to find the longest substring containing at most k distinct characters.
The sliding window pattern defines the boundaries. You have a left pointer and a right pointer iterating through the string, expanding and contracting to form a window of data.
Right.
But the window itself doesn't actually know what is inside of it.
Exactly. The window dictates the structure, but the hash map optimizes the lookup. As your right pointer expands the window by pulling in a new character, you use a frequency map to log that character.
Right, you map it.
And if adding that character pushes your distinct character count over the limit k, your left pointer starts shrinking the window, decrementing the frequency of the characters it leaves behind.
So the hash map basically acts as the real-time ledger for the sliding window.
That's exactly what it is.
You combine the boundary manipulation of the pointers with the instant lookup of the hash map to solve a highly complex, multi-layered string problem in a single linear pass.
They're deeply integrated patterns, and this foundational logic extends far beyond just Python scripts. The mental model you are building right now applies directly to data engineering and distributed systems.
Think about SQL.
Oh, yes.
When you are writing advanced queries, you often use window functions, like count star over partition by user id.
Right.
The database engine executing that query is using the exact same hatching logic we just discussed.
It is. When a database encounters a partition by clause, it doesn't scan the entire table linearly for every row.
No, that would take forever.
It reads the data into memory, applies a hash function to the partition key, in this case the user id, and streams the rows into specific memory buckets.
It is grouping data by a key, which is mechanically identical to building a frequency map.
Exactly identical.
And if you are working in a distributed computing framework like Apache Spark, this is exactly how data shuffling works.
Yep, the MapReduce paradigm.
Right, MapReduce takes a massive data set, applies a hash function to the keys, and routes the data across multiple physical server nodes so it can be processed in parallel.
So you aren't just learning a neat trick to pass a coding test here. You are mastering a core principle of computer science.
That's the real takeaway.
Hashing is how we map massive, unpredictable data streams into organized, instantly accessible memory addresses, whether that's on a local Python script or a distributed cluster of GPUs processing training data.
Okay, let's consolidate the mission here. You can now step into an interview and immediately recognize the trigger words for frequency and existence problems.
You've got the radar for it now.
You understand that replacing a nested loop with a hash map drops your time complexity from O of n squared to O of n.
You have the .git syntax memorized for safe state tracking,
Yeah.
and you know how to signal precision by utilizing a set when you only need to verify existence.
And most importantly, you can articulate the underlying mechanics of modular arithmetic and direct memory indexing to actually justify your space complexity trade-offs.
You are ready.
You have the tools. But before we wrap up today, we want to leave you with a provocation. We want to give you a scenario that pushes this O of one lookup logic to its absolute limit.
Oh, I love this one. Research the algorithm challenge known as subarray sum equals k.
Subarray sum equals k.
Yes. It asks you to find the total number of continuous subarrays whose sum equals a specific integer k.
Okay, but you can't just use a standard hash map for that, right? Because you aren't looking for a single complementary number.
Right.
You're looking for a sequence of numbers that might be 3, 4, or 50 elements long.
Which is exactly why you must combine the hash map pattern with a technique called prefix sums.
Ooh, prefix sums.
As you iterate through the array, you maintain a running total of all the elements you've processed so far. This is your prefix sum. At each index, you store that running total in your hash map.
Wait, so what is the complement we were looking for in the math then?
You check if the current prefix sum minus k already exists in your hash map history.
Oh,
Yeah. If it does, it mathematically guarantees that a continuous block of elements summing exactly to k exists between that historical index and your current position.
that is brilliant. It is an incredibly powerful architecture that maps continuous data segments into O of 1 lookups.
It really is. Spend some time breaking that down.
Yeah, understanding how prefix sums interact with hash collisions and state tracking will fundamentally alter how you approach array manipulation.
Absolutely.
And next time you find yourself staring at a whiteboard, remember the underlying mechanics. Don't build nested loops to scan historical data. Build state.
Calculate the complement and execute a direct jump to the memory address.
Thanks for joining us on this deep dive from the AI and ML mentors at 60 Seconds Academy. Go apply this mental model to your architecture designs, and we'll catch you next time.